Welcome to panel session 3, or paper session 3, our last paper session of the conference. I think you can see from the titles of these papers that we're going to see a lot of emerging themes around collaborative systems and live coding. So we're going to take the same format we've been doing, 15 minutes for each presenter, and then save questions for the end. And hopefully, because we have these emerging themes, we'll have lots of overlapping questions for this group. So first we have Mick Grierson. So take it away.
Hello. How are you doing? It's great to be here today. I'm having lots of fun. I wish I could have come earlier, but I was at work. And yeah, less said about that, the better. But the concept that we just witnessed was really fantastic. And one of the things I was thinking during the last session, Shelley Knotz's session, was how awesome it is to be able to collaborate in real time with people to make art. And there are an awful lot of technical challenges. And they can affect and impact on the way that people engage with interactive media, particularly today. And this is a problem that we've been thinking about at Goldsmiths for some years. And this problem has sort of manifested itself in a kind of solution, and we call this solution Code Circle 2. Now, I guess the obvious thing here is, what's Code Circle 1? We've never heard of Code Circle. Well, Code Circle 1 is a bit shit. So, I don't know, it was like we've been trying to do this for a long time, and our second iteration is the one that we're prepared to talk to people about. So what I'm going to do today is I'm going to lay out the basics of what the questions were before we started, what was driving us to develop this platform, and then we'll just look at the platform, because that's more fun than me talking. Well, I hope it is anyway. So I'm this person. Some of you know me. That's me. The reason this slide is here is just in case you don't know me, and to say that we're hiring. We're looking for 2 new postdocs very soon. You'll see the jobs go out. We really are focused on sound and image. We're a computer science department, but we have very much an arts focus. So if you're here today and you finished your PhD and you're looking for somewhere to go, come talk to me. So Code Circle 2 is a platform for creative coding. But it's also a platform for audiovisual art. And my background is as an audiovisual artist. And the things which have driven us at Goldsmiths to develop the tools that we use for teaching have really been focused on this one question: can you make audiovisual art with it? Because audiovisual art has a series of special requirements. Okay, there are things that you need to be able to do to make good audiovisual art. And for us, that was an easy benchmark. Look, is this tool useful for allowing us to do simultaneous digital signal processing for sound and graphics in real time? Can we do that? So audiovisual signal processing through textual code. So that's the other thing that we're focused on. This kind of creative coding idea, it's separate to existing paradigms, such as other kinds of graphical paradigms, such as you see in things like pure data and 4V. It's a different approach. It's really about programming using a sort of some form of textual language. So audiovisual art, just a bit more about that. The reason why I think it's a good test case, a good kind of way of focusing the requirements, is because a lot of rarefied forms of audiovisual art have the following elements in common. They're very abstract. Okay, so what that means is it's not representation, it's not filmmaking. It's not like, oh, well, we could just make a film, we could do it in non-real time. No, it's not about that. It's about the process of trying to make an artwork which is about formal relationships, often. Not always, but often. So the formal characteristics between sound and image are a kind of aesthetic preoccupation for audiovisual art. And that's interesting if you want to do signal processing, okay? Because it's an interesting set of questions. How do we do that? Also, a lot of audiovisual art's unified, so neither sound nor image carry meaning without the other. Now, a lot of the examples I'm going to show you, they won't be this, okay? What I'm saying is that this is a kind of guiding principle. Can the platform do this? Because many platforms can't do this, okay? They can either do one or they can do the other, but they can't do both at the same time. So this was an abiding condition. So that helped us to figure out what the issues were, what we wanted to achieve. And we wanted the focus to be on pattern making with code, right? So pattern making in sound and in image across both modalities and combined. So they're aesthetic concepts. They're not technical ideas that we want to achieve. Sure, they have technical requirements, but it's not the technique that drives us. It's this idea of can we actually make patterns and explore pattern making across these two modes of expression simultaneously. So what do I mean by pattern making? Well, I guess really I'm talking about periodicity, just to go a bit deeper. And so there are two ways of looking at this. From the image side, we can think of this as a sort of texture synthesis. And from the sound side, we can think of this as a kind of timbre, or timbre, depending on your pronunciation, synthesis, right? And in those two approaches, we're thinking about pattern in a different way. We're not thinking about pattern as in 1, 2, 3, 4, 1, 2, 3, 4. We're thinking about pattern in a different way, such as the surface of a pebble dash wall, or the way that sandpaper feels, or the surface of an expanse of water. Patterns on a very deep level, not patterns in a level of just everyday, oh, I really like that checkered blue and yellow square. I mean, maybe it is that on a basic level, but I mean, in terms of the actual, the quality of something. So this central notion of pattern goes right down to the periodic level. It's spatial and temporal, right? So I'm getting a bit abstract here, but I thought it might be suitable. So when we listen to a sound, it's made up of all these different periodic elements. When we look at a visual pattern, it's two expressing periodic elements. But one is spatial and one is temporal. And we want to be able to control things at that fine level, right, aesthetically. So periodicity, it's kind of a digital signal processing issue. So this is the problem. It's more efficient to exploit these kind of qualities and to explore these qualities through digital signal processing than through other means. It's good fun just to paint, and it's good fun just to play the guitar, but that's not, for me, that doesn't constitute research in this field. It can be, but for me it's not. I could have stayed at home, painted pictures, and played the guitar, but I wouldn't have been satisfied, right? So digital signal processing is a mechanism by which we can explore these aesthetic concerns. That's my arrogance, right? That's the thing that's driving it. So DSP is often just code, right? It's raw code. Max MSP and PD, they're insufficient to allow DSP at the required level to exploit real formal relationships. Not always, but often, okay? It's quite difficult to dig down into PD or Max MSP and really control every aspect of every buffer, of every input and every output. But you need that level of control to really explore periodicity. You can do it, but it's hacky and difficult. Most people find it a pain. It's a pain in the arse, in fact. Yeah. So textual code makes it much easier. You can write straight into the buffer. You can create images by thinking about patterns in a more embodied way. Well, actually, is it an embodied way? No, actually, it's not. And this is the issue. Why code is hard? I appreciate this is like a bit of there's also so many assumptions behind this, so I'm prepared to be strung up by them. But I'm just going to have a go. We type commands into a box, we wait, something happens, and it's usually the wrong thing. And this is awful, but this is most people's experience of textual code. Tappity-tap, tap, go, shit. Tappity-tap, tap, tap. And it's not a very embodied experience. It's very disembodied. It's separate from our experience. It's wrong. I would say it's wrong. Fields of HCI research, such as interactive machine learning, show us that this is probably stupid. This is not a good method for understanding. Why not make code embodied and sensorial? Okay? Why not design art and code interactively and even collaboratively? The way that I invite people around my house, we jam. Why can't we do that with code? So, yeah, this is all boring. Let's have a look at some good examples of people who do this. Live Code Lab, this really turned us on. I think this is a great little project that is brilliant for kids, but it's actually great fun for adults as well. But it's a good example of some of these questions, right? It's a live coding-inspired platform for education. It has a very simplified syntax based on CoffeeScript And my son, who's 6 years old, really loves it, really enjoys it. Doesn't have any idea what he's doing most of the time, but actually can just about grasp the basic concepts. And then he forgets them because that's what you do when you're 6. But he can use it, right? And so that, you know, I got in touch with them. We had a kind of a relationship. We sort of talked about methods. We had seminars from the team who were building this, and we thought about it a lot. Also, GLSL Sandbox. Have any of you come across GLSL Sandbox? I used to live in this piece of software. I love this so much. I can't tell you how much I love this, okay? Because you can make it's just shader, you know, GLSL, OpenGL shader code. If you're interested in graphics and you just want to do frag-based shader code, you can just like type and immediately things render straight away, and you can really understand what you're doing. You can really understand the expression of the parameters you're altering, and you can make intuitive leaps. And we were all like, yeah, we want to do this. There's Gibber as well, which is like fantastic, a really fantastic system. And in the paper, we've evaluated these platforms to some degree to say why we thought they weren't quite what we were trying to do. So this is the proposition. Discourse, copying, and error making are fundamental to learning. It's just a hypothesis. I'm not dictating this. You know, I'm prepared to be wrong. Our system encourages real-time discourse, real-time example making, and real-time errors, right, that are more understandable. People work together, even simultaneously, to explore complex, dynamic, mathematical, abstract processes. And we're sort of proposing a system which is like jazz improvisation, where the experience becomes non-verbal and maybe non-symbolic, experiential, where copying and modification is required and necessary, and where errors can be new opportunities. So that was the idea. That's what's driving us. Okay, and these were the goals behind the design: an environment for teaching programming that has a low barrier to entry, a high ceiling, so you can do anything you want that's possible, a simple method for allowing other forms of representation, so you could just put any language in you liked. You didn't have to use someone else's language. You could use your own language if you wished. It wasn't prescriptive. Not just a language, maybe just about interaction. And so this was the question. Maybe languages don't help. Maybe processing is great because it makes it easier, but maybe it's not easy enough. Maybe the interaction is the problem, okay? And then also we wanted to have this collaboration at a range of levels. And this is when we stop looking at PowerPoint, which is really boring, and we look at the platform. So the platform has about 450 active users at the moment. We're just doing a small pilot test. And it allows you, so every time I look at this, there's more stuff being built. There's a lot of people using it. I just saw this, which is an example built by a student in Los Angeles. To show everybody how to use the filters. I'm just checking out the room. It's a nice room. And so, yeah, so the idea is that what you can do basically is you can create an account. So this is my account. And you can create a document. You can make a document, my document. And you can use a template. So I can use this thing. So we have this thing in Goldsmiths, which Chris Kiefer helped us to create and maintain, called Maximilian, which is an audio signal processing library, which is a bit more flexible than web audio. It's written in C++, and we've converted it to work in JavaScript. And you can just grab this template. It loads that library and creates the new document for you. And then you have something which looks a lot like processing. And give me 1 second. If I put it in play mode, I now have complete control. Now it's running, basically. It's running so I can alter any of these parameters. I can change the frequency. I can create a variety of very simple tones very easily. That one you're not going to hear. We can create another oscillator. Well, let's just do my osc2 equals new maxim js.maxi osc. Here I am. And then we can, yeah, maybe I can stick that in here, plus, yeah, here we go, my ask2 dot, this will be funny. Don't know what will happen here. So what it's telling me is that I've made a mistake here. There you go. So I don't know if you saw that, but I had this, this thing here. MyOS2 is not defined. I've made a mistake here, and that's because I've not written, oh, MOSC2 is not defined. So I've written the wrong thing. So it's telling me exactly what's wrong. I can change it, I can add it, and then I've got something happening, which is great. I can now mess with it. What's going to happen? Yeah, okay. So now I've got a frequency FM system, which I can explore. Okay, and likewise I can load samples. So let me see, I can do, oh, here's a Shepherd tone test. This has been done by a student. I don't know if it's any good. It will have happened. We've got, this is a wooden box. Oh no, no, I don't know what this is. I clicked on the wrong thing. What's this? It may not run. Oh, here we go. So I can interfere with this now, and you can see if I click on this little icon here, this person has forked this document from a document that I created and used it to make their own thing. So I can fork it myself. I can say, get off. And I can make it private. I can create the document here, and I'll open up this document. It will run exactly the same way. And any assets just get copied across. And I can load sounds and samples. And then if someone else, if I sent that link, I could immediately, so if I sent the link to this document, I could post it to someone, and you don't have to have an account, you can dive right in. And if you create an account, it's just this link here. So I can paste that link in, and it will go straight there. And if I have an account, I can start to edit it and see the other person editing it in real time. So it all happens like magic. The other thing is, one more thing I'll show you before I finish. You can do complete graphical systems as well. So the audio is there, and then all of this stuff is also here for doing. Yeah, this is a fully fledged 3D rendering engine written entirely in the JavaScript canvas without any OpenGL. And you can just drop in and you can have a go with it. So it's codecircle.com. It's a very, very simple platform. It allows you to do complex things. There's a lot of good examples. It's currently being used live on this MOOC, which is running on the Cadenze platform. There are 2,500 people enrolled. So you can dive in and you can see examples of how to use it. And our proposition is that we use this data to explore different forms of interaction to see how we improve the platform. There are lots of other features which I don't have time to show you, but that's basically what it is. Thanks very much.
Great, that was fantastic. Thank you, Mick. And next, setting up, we have Bill Su.
Okay, thanks, Kate, and thanks to all the ICLI organizers for inviting me to participate. It's been a really great experience. And so this presentation is really an excuse for me to share some collaborative work with people that I really love working with and whom I think are really amazing musicians. So I was just going to play a few videos, but I'll talk a little bit and we'll spend a lot of time looking at videos, I think. So I'll talk a little bit about background and themes and related work and maybe look at a few pieces. So, so I'm going to talk about some interactive audiovisual systems that I've used with improvising musicians. Some themes, and so the idea is to, my goal, years ago when I started working on this stuff, is to build some systems that will work with improvising musicians whose work I really enjoy and admire. And the idea is to have these systems be responsive certainly to the audio from their performance, and also to gestural input from myself. And I am a big believer of leaving the human in the loop, because a lot of times we can make aesthetic judgments better than our code. At least I think so. So maybe my code is not as good as it should be, but that's my experience. And so something that I keep in mind is I try to make sure, because I'm working with free improvisers, that the visuals should not over-determine the narrative of the piece. And the idea is we'd like the conversation to develop organically, okay? So the visuals should really be an additional player, so to speak, in a performance. And so I mostly use generative abstract visual components, okay, and that have a range of behaviors. And so they allow us to develop a conversation as the performance progresses. I really like unstable forms that evolve, and and I'll talk a bit more about that. And I use very little pre-generated materials. A lot of my work actually evokes natural processes, and this kind of this kind of ties back to some of the wonderful keynotes we heard over the last few days. For example, when we look at when we think about a pool of fluid, and we drop some colored dye into the fluid and we stir it. Okay. So the evolution of the forms in the color and the colors in the fluid are very complex and unpredictable, but they have this high level behavior that we recognize in some way and we relate to. So this is kind of reminds me of Stuart Nolan's keynote when he talked about using recognizable objects in magic and having these recognizable objects do magical things. And that's one of the things that I think, I think of, when I play with these simulations of natural processes. And another aspect of working with natural processes is the process itself has a mind of its own. Okay, the fluid will behave, like a fluid, and we cannot, force it to do exactly what we want. We have to work with the way the fluid flows and the way the colors evolve in the fluid. And so when Roman Pasca was talking about the resistance of the puppet, that's something that again, I can relate to a lot, because a lot of the systems I build, they're not, you cannot control the details through either gestures or through the audio input. The musicians right away learn that they are not drawing the visuals, they're interacting with it, and they have to work with the resistance of the system. So some goals for the visuals, they should evoke the kind of materials that free improvisers tend to work with. They should be very tactile and nuanced, and the gestures should be temporally very rich. I usually try to avoid really simple mappings, and so when Michel Chion talks about Mickey Mousing, when you have a sound effect essentially that ties very strictly to a visual event, I try to avoid that, but there should be very clear cross-referencing, I think, between the audio and visual events, and whether I succeed in specific pieces is another question. And also, because free improvisers work with a variety of materials and also sonic space, so the visuals should also be able to incorporate a wide range of visual spaces. And my setup is something like this. It's fairly typical. Okay, so there's audio input from the musicians, and so the sound is analyzed with various with Maximus P, and various descriptors get sent to the animation environment, which also responds to gestural controllers, and and then video comes out of it, and also sometimes sound, depending on the system. So again, this is a very typical setup these days, and I'm sure we've all seen a lot of work using these setups. And again, I'm not claiming that what I do is particularly technically original or challenging. And I think a lot of what makes some of these pieces work better than others is the very specific design decisions we make in the context of the piece. And I'll try to talk a little bit about some of those and really the examples. Playing the examples is what this is about, I think. Some related work, so it's probably the clearest antecedent of all this is Golan Levine and Zachary Lieberman's Messa di Voce, which came out in 2004. And this is a collaboration with two vocalists, both master improvisers, Joan Le Barber and Jaap Blanc. And the piece is 12 sections over about 30 to 40 minutes. So the durations the Levine and Lieberman work with tend to be much shorter than the typical improvisation with the musicians that I tend to work with. And so the visuals are audio reactive, okay, to the performance voices. And camera-based tracking is used. Okay? So the performance bodies are actually a very integral part of the performance. It's very theatrical, and the suite is very theatrically effective. Okay? And so my own work is not as well. The visuals is really mostly confined to the video projection. The musicians tend not to have the gestures do not affect the video. Okay? And in free improvising concerts, while we do see the improvising musicians, a lot of times, that's not the point. Okay, we see the musicians to see, to actually recognize gestures, instrumental gestures and so on. But the point is not to watch them like you would watch an actor. Okay, that's not something most of the musicians I've worked with are interested in. So it's kind of a somewhat different approach, I think. But there are interesting video clips from the earlier work as well, and I think they look a bit different. And there are also other practitioners in working with improvisers now, working with visuals with improvisers. William Thibault, who doesn't travel outside the Bay Area a lot, is a particularly exciting artist. So let me talk about a few pieces here. So Flu is one of them. This is based on a smoke simulation, okay, and this will maybe make some of the goals and ideas more concrete. And so basically, the basic idea is there's a grid, and it's black, and smoke is introduced to it. Okay? And basically, each musician affects one source of smoke. Okay? And then the audio, how they play affects how the smoke sources move through the system. And there's a little extension that I make. I put hidden containers into the space, so the smoke can actually congeal into forms that are actually predetermined. And let me play a little bit of this. This is actually a demo, so it's not an actual live performance, but you get the idea. But this, anyway, here it is. So that there are actually two, this is a duet between saxophone played by John Butcher, who some of you might have heard yesterday, and also there's a noise generator that's actually from an automatic improvisation system that I built. But that's really a totally separate project. But what this is, what this shows is the two streams of audio affecting the smoke simulation. I think it should be pretty clear what's going on. Okay. And so another piece that I like to talk about, oops, sorry, how much time do I have? I just lost my timer. 4 minutes, okay, thanks. Is Xenoglacia Leishmania. This is a collaboration with Chris Burns. And so Chris builds these really great generative live electronic systems, sound systems. And I built a visual system that works with it. And some of the interesting problems here is Crystal Systems works with 6 tracks of and layers of electronic sound. And this makes it very difficult for the audio analysis software to actually pick out the important events and so on. So in addition to the audio analysis, we actually exchange network messages. And so he tells me on a high level what his system is up to, and I send him network messages that describe at a high level what my system is up to. And so a quick demo here. So I was going to talk about Fugue State, but I don't think we have time. And those of you who were at the concert last night saw this, and sorry, I can't even talk about I have another interesting Stuart Nolan reference, but sorry. So thanks to all my musician collaborators, and this work would not happen. It would not be where it is, without all the time and energy. John Butcher, Gino Robert, Chris Burns, and so on, and some of the venues their work was presented at. Okay? And really, one last note, I think a lot of what makes some of these pieces work better than others is really and why things are done in a certain way is the practical considerations of touring with musicians and working on them at short notice. And I'm happy to mumble more about this later, but so that's it. Thank you.
Thank you so much, Bill. As you can see already, building systems is clearly coming out as a theme for this panel. And now we're going on to another collaborative system, I think, yes?
No.
Not a collaborative system, just kidding. All right, so here we have Gerard Roma, who's going to present his work.
Okay, so bad thing about this session is that everything interesting I was going to say has already been said by the other presenters. So this is about an environment for synthesis-oriented live coding in SuperCollider. So I'd like to start with the basic like traditional abstractions in computer music languages, right? So just a reminder. So this is what is used in most computer music languages. First, there's the unit generator, which is the basic building block that you use to build patches or synthesizers. So the unit generator is like the oscillator or the filter. You build a synth definition or an instrument, and then you use some other abstraction to control the instruments, a score. You define patterns, events, and so on. And so when these kind of languages were started to be able to run in real time, the idea of live coding sort of emerged. And I have to say I was particularly skeptical about live coding myself. I was by then a software developer. So I had to practice to think twice about it and program very slowly and try to not to introduce any bugs. And so deadlines are basically the main source of stress in this context. And the last thing I wanted to do is to do this in a stage. Then the idea of introducing constraints to this kind of environments and domain-specific languages for programming musical events like Tidal or XLM, I think they create a much easier way to avoid the kind of failures that you could have in doing live coding. Of course, not musical failures, which is something that you still need to allow for, but at least programming type of errors and runtime errors. And I think, so these kind of environments are very well suited for what I would say the main applications of live coding, or at least the main applications we've seen so far, which is live performance and also classroom, where it's very useful that students can see somebody programming and they can grasp the mental process in this way. But of course, these environments, overwhelmingly, the majority is basically centered on the idea of musical events. And that really doesn't cover all the types of music that you can do. So I myself was more interested in kind of textures and timbre, that sort of music, timbre exploration. And so the idea of synthesis-oriented live coding, I think, could be opposed to the traditional event-oriented live coding. And of course, this is hardly a new idea. There is a very long tradition of challenging the idea of the instrument as an abstraction that is necessary when you're basically doing everything with a computer. And this tradition goes back to the pioneers in the Institute of Sonology in Den Haag, saying that essentially from the lowest level in the binary or sample level to the highest level abstractions, you basically have a continuum that you can decide how to partition yourself. There's also a long tradition in SuperCollider where most people, not most people, but a lot of people are very interested in how to do all music in the server side, and just by doing synth definitions. And one of the reasons for that is that the language that you need for that, the amount of concepts of the programming language is very limited. You only need to know how to combine unit generators, and you have a lot of them. So it's quite powerful to work in this way. But of course, in SuperCollider 3, the language was split into a server and a client. And yeah, this syntax that was used in the previous version was quickly recovered as backwards compatibility mode. But still, so you can still use this to define synth definitions and play them, but still for most practical applications, you need to start understanding about this distributed architecture. And I remember trying to introduce SuperCollider to engineering students. In this context, basically, it seems that the thing to do was to specify something and have them make a program that would accomplish a certain task and then finish. So for doing this, you would have to start the server. But of course, this is an asynchronous operation. It's in the network, so you have to wait for it, and then you have to pass it an anonymous function. So then, in this anonymous function, you have to define a synth definition. And these many new concepts that they had to understand, and at this point, they would say, okay, can we go back to MATLAB or whatever they were familiar with? And so, so this started to form the idea of making an environment that would constrain the interface to basically building synth definition in SuperCollider. So just using the part of the SuperCollider language that you need to build a synth definition and basically hide all of these asynchronous operations and provide graphical interfaces for them. Of course, this builds on the traditional prototyping interfacial development environments. So, namely processing and all of its descendants. They certainly the model for these kind of things. That they basically this kind of interface it constrains you to build like short programs. Essentially, if you want to do something complicated, you go and open a different type of environment and do an object-oriented program. But this is basically based on providing some API, some set of functions that hopefully provide the appropriate compromise between simplicity and power. So, and other related work, basically constrained environments in education. So there are many environments, for example, Sonic Pi or EarSketch, that offer graphical interfaces for coding. Mostly they are still event-oriented, so they're still based on learning how to program and making generative music, but not changing the sounds themselves. And also, of course, the idea of adding widgets in live coding environments is also very old idea, and some examples include Miniodical, the interface for Chuck and Jiver. So this is basically the main interface for colliding, which is this is kind of processing for making SuperCollider synth definitions. So I'm going to try and demo it. So basically we have like several tabs, and each tab you can define what is assumed to be a synth definition. So it's compiled and then wrapped and then sent to the server for you when you press play. Hopefully not too loud. And you can have like several of them playing at the same time. You can use change. So this slider is connected to this amp variable, which is predefined by the environment. And yeah, you can, I don't know, you can have some help, somewhere. And there's a panic button to stop everything. And it's basically just an interface for making it easy to create this kind of synthesis-based coding. Well, this seems stupid, but you know, error management is something that it's quite crucial for both in classroom environments and in live situations. So this is kind of stack trace that you get when you do some mistake. And this is the last thing you want to do to see either in a live performance. And also in the classroom environment, generally, the stack traces of object-oriented languages are perhaps more useful for teamwork and things where different people have different objects, and therefore you want to know who made the mistake. But here, so in this environment, basically you only get like the line and the error message, which is quite useful. Then, of course, the idea of using widgets combined with live coding sort of builds on the metaphor of hardware digital synthesizer, right? So this is the old, even the first digital synthesizers actually, they had a full computer interface with them. And all through history, they always required some sort of text input and output. So here you have this kind of little keyboard which defines some variables. So again, some implicit variables in the environment, the frequency and the gate. And so this is an example of a kind of FM synthesizer. And you can play some notes with the synthesizer just defined in this window. And for the moment, there are just these few like widgets for leveraging the computer itself as an interface. It plans to add a few more. Then there's also some facilities for buffers and files. As this is also typically asynchronous operations in SuperCollider. There's also a Freeman interface, which at the moment is not working because Freeman changed a little bit the authentication system, and also some basic project management. So to show you very quickly, so this is. So in SuperCollider you have like index buffers, so you can index up to 8 buffers and load some waveform. And yeah, you can play it, and then you can use buffer 0. We'll have this buffer here. And yeah, so how long do I have left? 4 minutes, okay. So I've been using basically this environment both in classroom environments and in live performance. In classroom environments, this was really, it was almost impossible to use plain SuperCollider. The motivation for using SuperCollider was that this was more in a music type of school where the students didn't have like a very strong programming background, but at the same time using graphical patching, I think it tends to favor the practice of just clicking around and connecting things without understanding much of what you're doing. And whereas coding, usually you're forced to give names to different things, and I think it's a representation that leads to a better understanding of the algorithms. So for learning synthesis algorithms, we're trying to introduce SuperCollider, but plain SuperCollider was too much for a course for learning enough to get fluent and start doing synthesis, different synthesis techniques. And with this environment, it's quite easy to get started, and then it's possible to explore a very wide range of techniques, because of the extensive library of unit generators you have in SuperCollider. And of course, it's also multi-platform free, and therefore it's very convenient for dealing with students. And also in live performances, so I tried to use this for basically improvising synth definitions and doing this kind of synthesis-oriented music. And basically, I would say it's still a bit more challenging than basically programming events and this kind of more like notation-like languages. Because the potential for failure is still higher, but still with this simplified environment, it became easier. And of course, I added like a personal additional constraint of basically learning a small set of unit generators by heart and learning all of the parameters, and then basically a set would be all the possible combinations that I could think of different unit generators. Also, the idea of having a scope of the server that you're playing with, and focus on small programs, and splitting the code into different windows for each synthesizer. I think it all helps really improving one of the main features of live coding, which is the readability of the performance. And so I have some future work. Basically, for now, I think the idea is working very well, but like there's just the basic features. So the idea is to add some more widgets. The same concepts that are implemented in the widgets could be very easily implemented as for MIDI controller as well, continuing with the idea of the hardware synthesizer metaphor. And then one very interesting avenue, I think, is the idea of encapsulation of synth definitions as UGENs. This is something you can do in SuperCollider, and I found some people, for example, Miquel Parera in Barcelona, who work this way. They define their own their own unit generator as a very complex synth definition, and then in the live set, they only need to use the unit generator, which is basically using the simplicity of using unit generators. And this allows you to build like a personal palette of sounds, and then you can, of course, keep building different abstraction levels using only unit generators. So this seems it would be very appropriate for this kind of environment. And then, yeah, there's some bugs, of course, and some missing features in the project management, for example, which is very primitive. And yeah, I'm going to leave it here. And if you have questions, I'll answer them later.
Thanks so much for that. That was perfect 15 minutes, by the way. And last, before we go to questions, we have Anna Xambó.
So welcome, and I'm going to present this research on challenges and new directions for collaborative live coding in the classroom. And just to say that, well, we can say now that live coding is an established practice, and there is research now on how beneficial and useful can be live coding in a more classroom or educational setting. And so we've seen now Gerard presenting colliding. There are other examples too. There has been a recent special issue on live coding and education and in this journal called Music Technology and Education. And so there are different environments discussed, including your sketch, which I will present here, but also SuperCollider or Sonic Pi, and so on. So I would like to start first explaining what informs this work. And it's basically the current US educational context in which this year's sketch project that I will explain a little bit further sits in, then the own practice, and then a little bit of empirical work. So there exists now a number of national programs that aim to broaden participation in STEM, standing for science, technology, engineering, and maths. And so broadening participation, referring to this idea of there are certain populations which are misrepresented in STEM fields, including women, or Latinos, or Afro-Americans. And so the idea of a program could be CS for all, computer science for all. And the idea is to try to get them, or have more representation. And so there is this kind of new educational approach, which is called STEAM. And basically it brings the arts into the STEM, and your sketch would sit into this. So your sketch basically, see the pointer, does it work? It's a National Science Foundation project led by Jason Freeman at Georgia Tech, and it's a big kind of project. And so it's a free environment that you can access via browser. And the idea here, it's based on the digital audio workstation kind of approach. And then you can learn to code by making music. So the parts are the code editor here, in which you can code using either Python or JavaScript. And you work with audio samples, which appears to be like a low entry level for students. And then you can run the code and position the different audio samples and apply effects that get rendered here in the DAW. You also have a curriculum which indicates or guides you through different exercises so that you can learn computing, but also music making, and computer music basically. Another influence of this work is existing practices on collaborative live coding. And there are a number of examples, but here just to mention a few of them. And also to mention that focusing on collocated groups and simultaneous interaction, which would, well, as opposed to, for example, what we've seen before with OFL, the OFL concert with Shelly Notes. So 3 examples would be, for example, small groups using individual screens, but they are sharing the same network. Another approach can be pairs using individual screens, but they are sharing a clock, and they are sharing as well a patch. Or larger groups with a shared clock, and who are able to modify each other's code. So we'll see, this is Pulso, which is a project in collaboration with Gerard. And the idea here was to share, So we are sharing the same patch, but we have different code editors, one for each. And this is built using SuperCollider, and also inspired by the XLang environment. The third leg that informs this work is informal conversations that we had with teachers who deploy your sketch. And we wanted to know basically what are the current practices in the classroom in terms of collaboration. How do they share the code how do they collaborate, and what are the teaching practices. And so we got a sense about there is a lot of asynchronous sharing practices, say, but we'd identify a need of more synchronous solutions. In terms of collaborations, teachers describe them as very organic and casual and different kinds of group, but still independent, potentially because also Sketch has this digital audio workstation environment, which promotes like more individual work, but they tend to collaborate. But again, we identify like this lack of, or more need to support the real-time collaboration. Finally, in terms of teaching practices, teachers explain that they prefer to promote peer-to-peer collaboration and learning, and they will just intervene if needed. So we wonder then, how would it be? And we need to be a little bit speculative here before deploying to the full school, right? So we are based on, well, with your sketch, you can already do some live coding. Basically, back to the digital audio workstation, you have the loop button, so you can just play looping your composition. So there is this kind of difficult fine grain between composing and performing. And then you can also define some loop points and soloing and muting the tracks. Then also considering how is the nature in the classroom, and this idea that there is this peer-to-peer collaborative learning. We would like to consider and respect this kind of way of doing in the classroom. Also situated learning and communities of practice in the sense that experts teaches to beginners. And also this idea that different kinds of groups can be formed. So for example, coders join with musicians, or again, experts with beginners. And so this is 3 approaches that we envision on how collaborative live coding can happen in the classroom. And 2 of them are more like pair live coding or pair programming based on pair programming practices. And a 3rd approach is more like multiple coders or live coders editing together. So live pair programming would be the most similar to the existing pair programming practices, which they already happen in the classroom. And so basically, the change would be that it's in a more live performance setting. So there would be still this driver and navigator roles. And basically, they would, they change in terms, right? So if you project the screen, you have a single computer projecting the script, then you can have a look or get a sense of these 2 clear projected mindsets. So the benefit of this approach would be that pre-programming can be explored in a more creative environment, but the script cannot be edited synchronously. An extension of this approach of pair programming would be in what we call pair live coding, which basically would be each student has 1 computer each, and they both modify the same script. Now, you can see that more as 2 drivers editing the same kind of script, which is interesting. There is simultaneous interaction. Now, there is a more fuzzier line between knowing who is doing what. So we can see that a more flexible approach to collaboration, but also can be more prone to errors. And we'll see this speculation in this kind of proof of concept. So this is Randall and Anna. So here we said, okay, each one will define a function, and then We communicate by comments. Comparing to, for example, what we've seen with real-file performance. So here, comments are mixed with the code, and it's the same color. So we were wondering whether like a more communication tool would be useful for chatting. And another approach would be like the extension of this, which is the multiple live coding. So the approach would be working as a Google Docs, but it would be like a script instead of a coding script. So multiple students can edit the same code, but question is, how do you know who is doing what? So it has a potential of interactive learning in a larger scale, but then also it's prone to more errors and more chaos. And we can see another proof of concept here. There are 4 live coders. Grows exponentially. So there can be some visualization problems as the session keeps going and going. But also with this proof of concept, only one person could run the code at a time, so it was difficult as well to know when to run the code, because sometimes there was someone just not finishing and then code was running. So yeah, there are maybe, it was good to see what issues and what are the potentials. So yeah, basically, what are the benefits? So we are moving from a more individual learning environment to a more social kind of domain, which looks interesting. And also, we are exposing students to new practices, not only like musical practices, but also coding practices and collaborative practices, which look interesting. Now, in terms of challenges, we wonder how to reflect pedagogically on this practice. How do we know that students have learned what they have learned, use this group kind of experience? Also, we wonder, how can we learn from watching simultaneous multiple live coders? So not only the students, but from outside, thinking of more like the live coding TV, whether this would be useful or not. So next stages, first we are interested in continuing this work and implementing like this kind of multiple editing kind of thing in your sketch. So this proof of concept has been good for that. And also we would like to explore more in terms of the curriculum, what kind of exercises can be useful for students. And finally, consider how to assess this kind of group collaborative music practice. So yeah, thanks.
Great, thank you so much for that. We have someone who's going to come around with a mic for questions. I'd like to start with one, though. So, Bill, you talked about how your interface was resistant, and Mick, you mentioned that you need failure to learn in your system. And Gerard, you said we put constraints on systems so they don't fail. And Anna, you said when we have multiple live coding, we have errors and chaos. So I guess my question is, do we build systems to fail, and why? It's for everyone.
I'm happy to go first, that's all right. Yeah, basically, when you build a system, it's going to fail. And you've got to build everything 3 times, minimum. And I mean, yeah, it was great looking at your research from the synchronous users, the prototype, because our system's synchronous. And when we did user testing with it, it was awesome, but total chaos. Fantastic. I mean, you know, in Code Circle, you can see everyone's name, but they just break each other's code for kicks. Like they just go into another person's document, and then if it's not locked, they just break it. And so, you know, that kind of, we had to make a decision about whether we were going to allow that, and we decided we would allow it. We would allow that kind of chaos for a while. But the truth is that we're working on trying to figure out how to prevent that from happening if people don't want it. And that means that's a design challenge. You know, it's about how often the script, because it's running all the time. It's running everywhere all the time. Social challenge. Well, yeah, I mean, you know, you can't stop people being a pain in the arse. And maybe that's a good thing. I mean, so it's hard to know what to do. We want to allow people the choice. So that's what, yeah, we're struggling with that.
So I would say we don't design systems to fail really, but maybe we design them to fail gracefully and fall like a cat, hopefully. And if they fail, not to break everything.
So I personally love systems that fail, but you know, within an educational context, we are now, for instance, focusing on or studying as well the errors that you were mentioning also, Gerard. The errors and how to improve the experience, so how to improve that aspect as part of the experience so that the failure shouldn't be seen as a failure, should be seen as part of the process, the learning process.
So I feel like the hard-right conservative here, since, you know, I'm the only one who's tinkering with my code at a time. But anyway, so in performance, for instance, you know, these systems, they're very complex systems and they will fail. And so I think that's where the human comes in. And, you know, that's where, you know, the human user will be cleaning things up, sweeping up the debris, you know, when things break. And so the performance can go on. Again, it's the show that has to keep going.
Yeah, I have a question mainly to Anna. You started out that one of the driving motivations for Earsketch was to get particular groups of people more interested in the STEM domains. So what I'm wondering about 2 things. Like, one is, did you actually do studies with Earsketch, like in these particular groups, whether it appealed to them? And my worry is a bit that the way you're constraining like the language and sort of the musical domain, like by choosing for particular musical styles, you might actually not reach the target audience that you're going for.
So, replying the first question, there is a study published 2 years ago on Earsketch showing, I mean, this study was in 3 schools, and there are significant results from the girls about before and after they getting more confidence into computing, and so this is a direction, and we plan for this next year that Earsketch is going to be deployed in a number of schools, I think more than 10. We plan to look into that even more, and in parallel, yeah, we're just interviewing some researchers and trying to fit this kind of route And in response to the second question, so basically it's on, it's a constraint working with audio samples, but then there are 4,000 audio samples in the library, but you're allowed to upload your own samples too. So that would expand a little bit, even though the constraint in terms of music genres. But yeah, I agree with you that it's constrained because of this design decision and also the looping kind of style. But I guess, in music and music interfaces and more in education, you need to put constraints. So we acknowledge that. But it's a good point.
My question will be for the first presenter, live circles. I think that there is some mismatch of what is live coding for now, because we maybe lose the roots of it. For example, when the liveness was presented in language like similar actor model, there was like you not programming but modeling, so the objects with changes with messages. And nowadays these are really read, print, evaluate, loop environments. So for example, you will get HTML language also in loop. It's actually a markable language. It's not live language, but you're actually live because it's in loop in your print. And so it's like not live coding, it's just environments where you could print live loop. For example, SuperCollider is live environment because there is object and messages. And so this programming in SuperCollider, for example, it motivates the coder just to program like he's as in 60s, for example. How was liveness was invented for? What could you say about this?
I think I'm not quite sure I understand, but I think if you're talking about our approach to kind of the embodied real-time approach as opposed to the kind of stop-start approach, and what is that the nature of the question? I think I spend a lot of time programming in C++ and I teach a lot in C++. And I fully understand that people, for certain kinds of musical approaches, it's nice to have a chance to break and decide when something is running and looping and decide when something isn't. And we have choices about that. I think what I've found, I'm in a situation where I teach computer science and I teach hundreds and hundreds, sometimes hundreds of thousands of people to teach to learn how to program. And we just found lots and lots of people struggled with that fundamental issue. Right, so it's not like we just, I'll completely accept that that people enjoy one way, that whatever way of working suits them, but those ways of working already exist, and we wanted to make something that, was for people who weren't very good at that approach or might benefit from a different approach. I don't know if I've answered your question properly, but yeah, I think it's, the notion of making things more experiential is at the root of what we're interested in exploring. And that means not really knowing what you're doing first, like when you grab an instrument and you smack it with a stick. You don't really think about anything, you're just smacking it, and then you're thinking about it afterwards.
Yeah, I was just thinking about the kind of the educational context, sort of imagining if I was like a music student and being kind of forced to code for the first time, I'd want to kind of have an experience which proved to me that I needed to use code, that it was necessary to use text-based code rather than some kind of graphical interface or something else. So, I mean, I think kind of, Nick, you made your case well for why use code, but I don't know, I was wondering kind of maybe sort of what your experiences were with students kind of saying, well, why can't I, go back to a graphic interface or something, or how, if you feel it's important to build that into your environment for all of you. For all of you?
So, I don't know, in my experience, there seems to be some existential fear of programming sometimes. But it's not I think it's more apparent than real, especially if you interact with young students. They're pretty open to do whatever is useful, and then the only problem is passing the course. But as long as you provide a path for doing something interesting, it's not such a big deal, I think. The problem is when you get stuck in something and you really don't understand what's going on, and that's why I think all of us here we're trying to kind of deal with this issue of providing feedback and providing an environment that allows people to progress and not get stuck in something that is overwhelming and it's not possible to understand.
So I think in the 21st century, it's important or it's a useful tool learning to code, as I would say, learning anthropology. So there are useful tools that are needed to survive. And it's good to learn them as soon as possible, in a fun way though.
So I've been using Dreamweaver since 1999, something like that, since version 1. And for me, now I never use the design view. When I first started using it, I only used the design view. And then I slowly swapped between the design view and kind of split between the thing. But the idea of the round-trip editing, that what you'd kind of add a div here and you'd see it appear in the code, but then you could monkey with it in the code and it would change back into the design view, for me was very liberating. And I wouldn't be doing what I'm doing now without that experience.
I think that's exactly right. So I think, yeah, it's quite hard to do low-level programming, and it's quite hard for people to, especially with audio, also with some kinds of texture synthesis. It's very hard to conceptualize what's going on when you're doing frequency modulation. It's tough. People can't get it. Computer science, I teach computer science. Those computer science students, they don't get it because they love discrete maths. They like sets. And then all of a sudden you're saying, oh, we're just going to add these two waves together. And they're like, why are you doing that? And it's like, yeah, well, and you say, okay, so we've still got one wave at the end. And you go, no, you've got two waves. No, you've got one wave. And they're like, that's not right, because we've added two things together, and that should be two. And it's like, and they can't, they say things like this in first year computer science, and you're like, yeah, this is going to be tough, right? It's going to be hard. And yet people who've got a music background find this really easy, because they've looked at a waveform plot, and they know that when you get two sounds and you add them together, you've still only got one signal, it's superposition. The thing does this, and you add another thing, and it does this, And so, we find that people with a natural experience find that more easy. But on the other end of it, they have to learn, if they're going to get a job in the contemporary audio industry, they need to know how to code properly. And when they ask me, why am I doing this? I say, because if you do this, I can get you a job. And it actually kind of comes down to that.
Yeah, it doesn't directly link to this now. I totally understand these constraints, but from a broader picture, I just wonder, so we're doing music, but the computer doesn't understand if we just sync to it, so we can't just dance with it and it gets it immediately. That's not how embodied we are yet. So we need to find some way of communicating with it. Now we've got the option of maybe using a visual language or code. And somehow I wonder, do you think that what's more removed from the audio or musical realm, the using textual encoding or a visual encoding which then is translated to text and then does music? I just wonder, are there some, wouldn't it be interesting to look for really new ways of interacting or of doing music by looking at computing which is not necessarily textual? Sorry.
So I think there's something interesting in text in that right now we're using language to communicate. It's a very effective way to communicate, also with a computer. But that doesn't mean that doesn't preclude other forms of interaction. I think it's very interesting that there are ways of programming visually, and maybe it's now the time to actually use more like tangible interfaces for also like kind of coding environments. So I think there's just different modalities, and they're good for different types of things, I guess.
I think a lot of people who work with sound start out in Max MSP or PD, right? So that's kind of the visual paradigm. And so kind of rambling on that note. I'm also my job is also in CS. I don't know why, but anyway. So I've taught programming students at different levels. I have a computer music class and with some students. And the interesting thing is the students who have experience with textual programming, and I throw Max or PD at them, and it takes them forever to get used to it. And but then so because of this, I actually switched to something like Porn MIDI, so that they're actually doing textual programming for the interactive MIDI project, and that's much easier for them. So I think your brain kind of gets wired, a certain way if you start out programming in a certain way, and I think Max and PD are really great because the major operations people tend to use for audio. Okay, so this is my opinion. Okay, sorry. The major operations that I would use, as an audio programmer, tend to be fairly well defined and kind of encapsulated nicely into these objects. But when I do visual programming, I don't have these nicely encapsulated major operations. So I don't think it's very hard for me to work in jitter, for instance. But something like processing open frameworks tends to be a more natural fit for visual programming for me. So,
I think that's all we have time for questions. So let's thank our panelists one more time. Thank you very much.